Hello student, today in this lecture we are going to study antenna and its parameter. So in this first slide I have defined the antenna or what is meant by the antenna. So basically antenna is a part of a transmitting or receiving system that is designed to radiate or receive electromagnetic waves. This is just shown in here the amplifier signal given to the antenna, and again at the receiving side the antenna signal is given to the antenna. That means at here the antenna is working as a transmitter of the electromagnetic wave, and at the time of the receive section the antenna work as to receive the electromagnetic waves. Another definition is made the antenna is a transducer which convert electric power into electromagnetic waves and vice versa. That means antenna itself can be transmit the electromagnetic waves or it can be receive the electromagnetic waves. It convert the electric signal given by the amplifier into the electromagnetic waves. Also, the antenna can be received electromagnetic waves and gives into the radio signals or the electric signals. So that's the basic definition of the antenna. That means the antenna is a transducer or the element which convert the electric signal or the RF signal into the electromagnetic waves, or it can be convert the electromagnetic waves into the electric signal. So whenever we are considering the antenna and its application, so its parameters are very important, because when we are using the antenna in the wireless system, so each applications the requirements of the antenna is different. I explain the two examples. When we are transmitting the radio signal for the television applications or the FM applications, that time the requirement of the antenna is that it transmit the energy for the long distance as well as it cover the large area. That means its region of coverage is must be have the high. So designing the antenna for that applications, the directivity and gain is considered. That means that time the its region should be the high. It cover the more area and directivity also the high. But when we are taking another application, that means for the satellite applications or the aeroplane application or the radar application, that time the antenna application is that it transmits the energy for the long distance, but its directivity, that is its focusing power, it should be the very small. That means if you take the first application for the TV and FM, if you take the bulb and you provide the electricity to that, so bulb radiate the light. So its light is radiate in the all direction. And for the second application, for the satellite or the aeroplane, the if you take the IR or the if you take the laser beam and you on the laser, so it concentrates the its energy only for the its focus point. It does not radiate its energy for the all direction. It only focuses the center point. So that is the applications of the antenna, and depends on the that application we design the application antenna. And when designing the antenna, so these parameters are the very important. So which are the antenna parameters? The radiation pattern, beam area, beam efficiency, directivity, gain of the antenna, antenna impedance, radiation resistance, beam width, bandwidth, polarization. So these are the parameters of the antenna. Now we are going to study the first parameters of the antenna, that is the radiation pattern. So radiation pattern of an antenna is the one of the its most fundamental properties of an antenna, and many of its performance parameters are related to the radiation pattern. How we can be define the radiation pattern? So radiation pattern is nothing but mathematical function on a graphical representation of radiation properties of an antenna. So what is the definition of the radiation pattern? So radiation pattern is nothing but the mathematical function or graphical representation of the radiation property of an antenna as a function of the space coordinate. That means when you use the electric energy or the electric signal to the antenna and it varies its energy into the form of the electromagnetic waves. Now how it radiates that energy is represented by this radiation pattern. So in first figure you are looking here is a horn antenna and we applied some electric energy to the horn antenna to the waveguides and this side it radiates the electromagnetic energy. Now how what is the nature of this electromagnetic radiation? So that's shown in the this. So this is nothing but the radiation pattern of the. So more detail we are going to study the radiation pattern. So radiation pattern is shown here. In this radiation pattern, it contains the beam widths. This that means the radiation pattern is divided into two parts. One is a beam widths. There are the two types of the beam widths. One is a half power beam widths and a full null beam widths. And second are the lobes. So there are the three lobes. One is a major lobe, side lobe, and back lobe. So first we are going to study the lobes. The first lobe is the main lobe, or it is also called as a major lobes. So what do you mean by the major lobe? So major lobe is nothing but the which cover the large area, or one can be says the major lobe radiate maximum energy into the specific directions. So that is nothing but the major lobe. Here I have shown the major lobe. So this is a major lobe. So in this second pattern here shown is the major lobe. So this pattern is nothing but the polar pattern. This is nothing but the linear plot of the radiation pattern. How antenna radiate the energy is represented in the radiation pattern. So this is the radiation pattern we have plotted. Actually the radiation pattern is in the form of the 3D. But for the simplicity we have taken the 2D image of the radiation pattern. This is both are the same. Only the difference is the representations is the different. This is a polar and this is a linear plot of the radiation pattern. And in this radiation pattern, so this is a major loop. That means radiated energy is concentrated into one specific direction. So this is a specific direction. So that is called as a major loop. Now second lobes are the minor lobes. So what are the minor lobes? So minor lobes or the side lobes are nothing but other than the main lobes. So this is a major lobe. Other than the major lobes, so these are nothing but the minor lobes. So these are nothing but the minor lobes, or minor lobes is also called as a side lobes. And third lobe is the back lobe. So back lobe is nothing but, so we are looking at this back lobes. So these are the back lobes. We are shown back lobes. Oh, sorry, here this is back lobe. So in this pattern you are looking the back lobe. So back lobe is nothing but the exact opposite of the main loop or the minor loop. So these are the loops. Now second is the beam widths. There are the two types of the beam widths. One is a half power beam width, which is also called as the HPBW, and second one is the FNBW. So this is a half power beam width and this is a FNBW, that is a full null beam width. So definition of the half power beam is nothing but it is an angular separation. So it is an angular separation. So this is angular separation. Angular separation in which magnitude of radiated pattern decreases by 50% or minus 3 dB from the peak of the main loop. So if you take this main loop, if you take the main loops and it's 50% we are taking or minus 3 dB. That means suppose this is a 10 something, its unit is a 10, and if you multiply this 10 by the 0.707, So we get something here. So this is a something here we get. And if you take the angular separation, if you take the angle, so this is nothing but the side. Sorry, half power beamwidth. So this is half power beamwidth. So this is nothing but at this point we are getting the half power of the radiated. Whatever may be it radiating energy. Out of that, this is nothing but the half power. And this half power beamwidth is often used to measure the directivity of the antenna. So this is nothing but that it's used to measure the directivity of the antenna. In this specific region, the transmitted energy from the if you take the angle of this straight like this and like this, if you take this angle, so that much area is applicable for the radiation of the antenna or the reception of the antenna. So that is nothing but the half power beamwidth. And second is nothing but the uh, first null beamwidth. So first null beamwidth is defined as the angular separation between the first nulls of the pattern is referred as a FNBW. So this is nothing but the FNBW. Angular separation between the first null. So this is first null. So this is first null. So this is first null. First null. So this is angular separation between the first null. So in this way we can define the radiation pattern. So next slide is the type of the radiation pattern. So when antenna radiates its energy, so its pattern is looking various shapes. So it depends on that there are three types of the radiation patterns. One is isotropic antenna, isotropic radiation. Second is a omnidirectional antenna or the omnidirectional radiation, and third is a directional antenna, or one can say the directional radiations. So in the first isotropic antenna or the isotropic radiation. So this type of the radiation is not exist in the real life. So this is a hypothetical. Hypothetical. So isotropic antenna or radiation is nothing but the hypothetical lossless antenna having equal radiation in all directions. That means when if you take the antenna here, so it radiates its energy into the all direction. The same example, if you take the light bulb and if you blow that, so it radiates the light in the all directions. So that is the radiations of the isotropic antenna. But in real life, such type of radiation we never got. So this is only ideal. And the calculations for the antenna parameter, we are considering we are taking the consideration, we are taking some help of the isotropic radiation, but it is not present in the nature or not present in this world. Now second is a omnidirectional antenna or the omnidirectional radiation. So figure B shows the omnidirectional radiation pattern. So this radiation pattern is radiate or such type of the antenna, omnidirectional antenna, radiates and receive equal in the all direction. That means it radiate the energy or receive the energy equal in the all direction in the azimuthal plane, that means horizontal plane, not from the vertical. So this is shown in the second figure. And third is the directional. So in this directional we transmitting the energy or receiving the energy in a specific directions. So it is defined as having the property of radiating or receiving electromagnetic waves more effectively in some direction than in other. That means such type of the radiation pattern, directional radiation pattern or the directional antenna transmit the energy in a specific direction, not for all direction. Now another important parameter of the antenna is the directivity of the antenna, and actually this property it states is tell about the antenna how it concentrates antenna radiated energy or how how focus its energy in a specific directions. So directivity is only related for the concentration of the energy, and more detail, the directivity of the antenna is defined as it is a ratio of radiation intensity in a given direction from the antenna to the radiation intensity average of all directions. And mathematical it is given d is equal to 4 pi u divided by p rad. So p rad is nothing but the total radiated power, and 4 pi is the sphere of the circle. Also, the directivity of the antenna can be expressed in the solid beam angle. So, solid beam angle is shown in this figure. So, this is solid beam angle, and the directivity of the antenna from the solid beam angle is given by d is equal to 4 pi divided by the rho a. So, in this equation, we can simply say that directivity is a simple ratio of the area of the sphere. So, this is the 4 pi is nothing but the area of the sphere to the solid beam angle. And as the solid beam angle is increases, the directivity of the antenna is decreases. And vice versa, if the solid beam angle is decreases, that means if you make the angle is small, that means its directivity is become the high. And next important parameter of the antenna is given by the gain. It is not same as the transistor gain. So it is again this parameter is related to the directivity of the antenna, and it is defined as the ratio of the intensity in a given direction to the radiation intensity that would be obtained if the power accepted by the antenna were radiated isotropically. And mathematically it is given by the 4 pi u theta phi and divided by the pe. That means basically the gain of the antenna. What is still, if you take antenna and you provide some energy to that antenna, now how it radiates the energy in a specific direction as compared to the same energy if you provide the for the isotropic antenna or the ideal antenna. So from that we are calculating the gain of the antenna, and simply the gain of the antenna is given by the efficiency and the directivity of the. It is simply the product of the efficiency and the directivity of the antenna. And note that the gain of the antenna is never greater than the 1, because antenna always possess some losses, and because of that it's never radiate more energy than its input. It always radiate less energy whatever we are provide the input, because some energy will be lost. So these are the some references for the these lectures. Thank you. So these are the some references for the these lectures. Thank you.